not quite so much. Okay. So this is also, to some extent, if you looked at it as a companion to Gustavo's talk. Unfortunately, while Gustavo got to present nice, happy, optimistic results, this is much more in the way of a negative, notes doesn't work result, which is, I guess, less exciting to listen about.
They were not so optimistic for the sharing.
Yeah, but the technique-wise, they were pretty optimistic and high RN and all sorts of fun stuff there. So, the question you want to ask is, why do we want to look at magnetic helicity transport in shearing systems? Well, the answers there are actually relatively straightforward. Shearing systems are interesting because they're ubiquitous in astrophysics, and basically all the astrophysical dynamos are believed to draw a large portion of their activity from shear. Unfortunately, it's also a system which, while dynamos can be looked at in the lab, I don't think any of the laboratory dynamos right now really use shear. And it's kind of hard to imagine actually producing a laboratory dynamo experiment where shear is a major player in the near future. Magnetic helicity transport is more difficult to justify. The problem here is that magnetic helicity is usually defined as a volume integral of A dot B over a volume, with B being the perpendicular component of B on the surface being 0. People frequently also use periodic boundary conditions and B going to 0 fast enough. Those are not actually entirely complete constraints for capital H being well defined. The only strict constraint that works is the perpendicular component of B being 0. However, you can't really talk about the transport of such a quantity. It's not a meaningful statement. So what we are talking about is the transport of magnetic helicity density, which of course is gauge dependent. So it's not obvious that magnetic helicity transport is all that well defined, and part of what we're talking now is some difficulties in really defining it in a useful fashion. One thing I can say is that we have found that the magnetic helicity contained in small-scale fields seems to be a reasonably well-behaved, relatively gauge-independent quantity. And most of the gauge dependence appears to occur at large-scale fields. And that is the component, the small-scale helicity component we're most interested in.
Let me ask a question. I agree with you that for small-scale stuff is not so important on these programs.
Yeah.
But if you've got dynamical equations, and you've got somehow some way how to calculate small-scale stuff, and this large-scale equation, I mean for mean field, gauge independent. So maybe it's not so difficult, how to say, problem. Maybe it's some, how to say, our feeling is so difficult. Of course, it's useful what you discussed, but maybe it's not so crucial.
I'm not 100% following.
Again, small-scale stuff is not so sensitive to gauge conditions.
Yes.
Large-scale, yes.
Large-scale,
but if you've got dynamical equation for small-scale stuff, unfortunately, we haven't any sign of A and B. We've got just small a and small b, and so in this sense, if you've got reasonable dynamical equation for b, you haven't any troubles.
That's more or less the case, yes.
Okay, it should be.
But there is more.
There's nothing crucial to the talk.
It's one of those things, also one of the things which is not particularly. Okay, so the big issue, or one big reason why we do want to look at magnetic helicity transport is because, well, we kind of want something like that. And simulating that is hard. Very, very hard. But we really want to simulate it for both on very small scales, so we can predict structures like this, which could then launch stuff which destroys our nice satellites, or potentially our power grid, or in the worst case scenario, Western civilization. We'd also like to be able to predict it on like 10-year time scales, just on a more climate type fashion. So what we're talking about more is the 10-year variability and the whole cycle variability and sort of the background behavior, whereas Andreas, if he's going to give any talks now, will be talking about the several hour prediction, which is perhaps slightly more crucial to our continued existence. But when we're looking at trying to model the sun, basically we have two options. One is we can do a direct numerical simulation. Well, we can't do a direct numerical simulation. It's kind of a problem. Or we can try and do simplified physics and maybe concentrating on one portion of the physics or another, which sees more detail and less exciting stuff for other things. So we just sort of maybe take average fields, probably phi averaged, and come up with dynamical evolution equations for them. And the problem there is you need to actually come up with some sort of simplified physics model to handle that. Shear is relatively easy to put in. Sort of an alpha effect is much more complicated, especially because you think that the dynamo saturation which occurs takes place in the alpha effect, which thankfully I don't have to explain here and define here. And that means that we have a lot of physics that actually gets wrapped up into that term. And we're going to want to figure out how to deal with that, and magnetic elasticity is sort of the way of doing that. So skipping this, unless anyone really wants me to talk about it. Once you've done your mean field decomposition, you can come to a nice set of mean field equations, where we need some sort of rule for the EMF. I'll also note here that shear is actually a tricky thing to handle. It has both the characteristics of a mean field and of a fluctuating field. For example, if you're having a shearing sheet, but you're averaging over sort of one period, your shear flow can average to 0, which suggests this should be a fluctuating term. However, its derivative of the uniform shear is unity, which would then be a mean value. So just know that shear is a little bit difficult to put into mean field equations, simply because the derivative of x is 1. So we're looking at helicity because of the magnetic alpha concept. I don't know, hypothesis maybe, which has been reasonably well borne out. That idea here is that you can decompose your alpha effect into kinetic and magnetic components. Of course, we also figure the fact that kinetic is poorly defined, as is the magnetic. And you make an assumption that the magnetic helicity, which happens to be a reasonably well-behaved quantity, despite its gauge dependence, is related to the current helicity. And the current helicity, unfortunately, is not a well-behaved quantity. Although, have you, Dhruva, do you play around with the current helicity stuff anymore? Or the current helicity, the J dot B times rho to the 2/3, maybe 2/3.
No.
Okay. Yeah, I don't have any. What?
It's not the growth motion. And
Yeah,
as a result, triple correlate is not flux. It's much a little bit more complicated.
It's a royal path. And the reason why magnetic helicity is sort of such a useful value is because of magnetic helicity conservation, where in the absence of fluxes terms are dropped, then you just have source terms, and the mean field dynamo is separating helicity. Did you have a question, or?
No.
Okay. So all this stuff is stuff that I think everyone here has seen about 20 bazillion times. This is where we may be going into new stuff. The magnetic helicity fluxes can be defined or found through this formula here, where this phi is coming from the equation for the time evolution of the magnetic vector potential. And this is why you're saying that your integral is only really defined over a surface with d perpendicular being 0, because that forces this term to 0. That's a gauge term. But if we can get a model for the fluxes, then we can construct an improved dynamical alpha quenching model, and we can run mean field simulations.
What do you mean that you average and bracket average? What's the difference?
Volume, surface, the overbar I've tended to work in planar average with overbars and volume average in brackets. So planar average over xy, and then you can move to a volume average, also averaging over z.
And this is total average in all the...
Yeah. Volume average versus a planar average.
In that case, of course, you don't have fluxes.
In that case, well, what's the terms here? Which are scary if you talk about volume averages, yes. So I probably should have, this is a hack, right? I probably should have been careful.
So brackets is going to... Oh, you don't need brackets. No.
I don't need brackets in this case here. Yeah, the brackets should be eliminated. So this has been used basically by Gustavo and Piali and Axel. Is Piali here? No. To look at the sun, and they can use this dynamical alpha quenching formalism. This right here is with an assumed diffusive flux of magnetic felicity to go to, well, RMs that are actually somewhat reasonable for the sun. But here is actually complicated, unfortunately. So the point of the paper that I'm supposed to be talking about was really to look at the Vishniac-Chov flux. It's a flux that's been calculated to exist in the presence of shear, alpha and omega dynamo. It transports magnetic helicity, small-scale magnetic helicity along the shear rotation vector, or whatever you want to call it. And it will produce a flux which is proportional to the shear and the difference between the horizontal fields. In this case, I have a shear velocity that's along y varying with x. And here I have sort of a butterfly diagram for an alpha omega dynamo, which we're looking at, and you see the nice pretty butterfly. This one in here, dy is much stronger than vx, as you can might be able to tell from the quality of the contours. And if you look at the fluxes of small-scale helicity, you get this. This is what we find in simulation. This is what the Vishniac-Chov flux from this formula will predict.
This is direct numerical simulation, you mean?
These are both direct numerical simulation. This right here is basically just applying this formula, and this is what we actually find. And you'll note that basically you don't see the Vishniac-Chov flux here.
So how is the left one defined?
The left one is defined by E cross A. And you'll note that there are some problems with defining it as such.
E cross A?
E cross A.
So E before average, you mean instantaneous?
No, it's the small scale fluctuation.
The small scale fluctuation.
That's important, of course. So that's exactly why the gauge
Yeah.
sensitivity of large scale fields is eliminated. Otherwise, it wouldn't work.
So which one is this?
So it's the small e cross a, small e cross a, small a. I knew I had a slide, but it might have been farther along. But it's the formula that comes out of the flux term for the small scale flux. It's probably on the next slide.
But this assumes phi equal to 0, or?
This assumes that there is no vertical phi component to the flux. Yes, no vertical gauge. There's no vertical term coming from the gauge. That's what it assumes. Perhaps even more importantly, this flux right here has a strong vertical divergence, and that's also does not show up here.
So this is a special distribution of flux.
This is an alpha omega dynamo in a shearing periodic flux.
So the x-axis is time actually.
The x-axis is time.
So that's why you get this traveling
Time.
envelope. See that?
Z.
The envelope is traveling in the direction of positive s times a.
Yes. So here we have the time traveling, the butterfly diagram, the traveling wave.
So on the left side, you plotted the total helicity, small scale helicity flux in that direction, right?
Yes.
But as I remember correctly, the Vishniac-Chov flux is only one part of the small scale helicity flux.
doesn't it?
A lot of copper.
It's one component of it, and that is one of the issues.
Okay.
What other component could be in this case?
Hmm?
What other component could play a role in this case?
I'd have to actually, like, there's a decent number of other components.
I think what you're
There's
referring
other
to is the
terms.
fact that we have also diffusive fluxes,
Fluxes.
and we have advective fluxes.
But the velocity is zero at the boundary, so we should have no effective.
Exactly. And
Yes,
that's
there
why,
should be no effective flux.
and that's exactly the answer why what we see here should be mostly be attributed to the Birch-Trou flux.
Mhm.
And the diffusive
Yeah,
flux.
potential.
No, not the diffusive flux really, because the alpha times magnetic electricity density is also
Magnetic electricity
uniform.
is pretty much uniform,
But
which is
what
another problem.
about gradient of alpha? Because
That's
with
what it is. It's
Gradient of alpha,
the alpha
gradient
effect
of
is
delta.
uniform in this domain.
two things, gradient of alpha and gradient of density maybe.
This system is very much uniform.
Density is
it's-
uniform.
There's no stratification.
Okay, so the gradient
And
of alpha,
it's triple-
gradient of alpha
It's
is
a
also
periodic, so it's periodic.
Even within the dynamo wave, it's
Mhm.
small, because that would go with
This is,
alpha with A dot B, and A dot B is
yeah, there is going to be some
Very
density
uniform.
Okay,
variation, but
but
it's
the
not.
alpha should be homogeneous, I think.
Oh, that's something which I will be talking about in a little bit. But
But it is the gradient of
alpha, sorry, yes, alpha is, it turns out, although it's something that we're looking at now, we just started to look at, how anisotropic alpha is.
Gradient of-
Druba did look at that prior, but unfortunately, I think the normalization had issues. And in the nonlinear regime, alpha turns out to be highly anisotropic, but that's not really the topic of the conversation.
Gradient of alpha is homogeneous, but the gradient of alpha m is not.
That's something which I'm going to be coming to in a
Gradient
little
alpha
bit.
m, it means in some sense diffusion too.
Yeah, becoming
So the gradient of alpha is homogeneous, so there is no gradient, there is no such diffusion. But for alpha m, it's proportional to b, to the magnetic
I'll be getting to that in just a little bit, actually. In fact, why don't I get to that now? So that's another thing right here. Again, I'm reproducing the butterfly diagram. So this right here, if you look at B, you expect there to be strong and vertically varying fluxes, which would generate, and with our finite divergence, so that would expect this to generate some sort of vertical distribution of helicity. Same here, this EMS.B term is also expected to generate strong vertical variations in small-scale magnetic helicity. It doesn't. This is a small-scale helicity. There's no particularly obvious. This one right here is corrected for the motion, but there's no strong vertical distribution of small-scale helicity. And that does.
Say again, what is it?
This right here is A dot. This right here is small a dot b as a function of height.
So it is butterfly diagram of what? Chemistically.
Yes, a dot b.
A dot B.
Small a dot b.
Smaller than this. It is practically
Uniform. There might be some tiny little bits, hints of signal, but I don't really believe.
So, in other words, all these strips become simply horizontal lines.
This right here is corrected for the velocity, for the dynamo wave. So all these things right here would be stripes here. This right here predicts vertical structure. This predicts vertical structure. We don't see a vertical structure.
What's happening at the end of the sun?
That may be where life goes crazy.
No, that's exactly what the stuff that you have been working on in the last few.
I can't remember exactly what this when this is correct, but this could be where the alpha omega dynamo decides to wander off into oblivion for reasons that we do not
It
yet
becomes an
understand.
alpha squared dynamo. Yeah, because of alpha quenching. So alpha is quenched, and you no longer have alpha omega.
It's not visible in the butterfly diagram.
Yeah, it's not. So that's why I'm a little bit wondering, but there might be some issues there. I'll go back. But it is worth noting that this is still
It's the same. It's
several thousand turnovers at an R of 90.
No less.
So
No less. Yeah.
Can you say something about this kind of bands? Do you have some?
there might be
reddish
bands, but I wouldn't want to really claim that I see much there. There were some bands at much lower magnetic Reynolds number. This is a magnetic Reynolds number of 90. There were actual significant bands at like Reynolds number of 4. which does suggest that this guy was playing a role. This guy may have been playing a role at Reynolds number of 4, and may still be playing some sort of residual role here. And that, of course, does raise the question of, these predict some sort of hot spot or hot band. This sort of this one, we don't see it. So to what extent this hot spot here, coming from where the maximum would be, is somewhat questionable. But what on earth is actually going on here? Well, now basically the idea is that shear can generate horizontal fluxes of finite non-zero divergence. And that's something which is not necessarily immediately obvious. We start with a shearing sheet, and then we imagine that it's shearing periodic. So we have a nice vector potential A bar and our magnetic field B bar, which of course then generates a U cross C, which is opposite on the two edges of our domain. And that in turn means that our flux is pointed into the domain. That has finite divergence. And that means that all of a sudden, we're going through a system, we're doing planar averaging, and we still need to track horizontal fluxes. Even in a shearing periodic domain, we're doing horizontal averaging. And that's a royal pain. And it's also coming from the fact that vector potential A does not actually have to be periodic, even if your system is periodic, or shearing periodic. Although you can make it so with an appropriate gauge transformation. So basically, all the stuff that's predicting small, like hot spots and where EMF.B is large, that's also cases, places where you expect there to be significant fluxes that are horizontal and have a finite divergence. So I guess this is where this was the formula here with phi equal to B was the formula for the flux that we've been using. But basically the idea is we don't actually know exactly how to treat fluxes of magnetic helicity in shearing systems. We have seen diffusive fluxes in other systems. The coefficient is wrong, but not wrong by sign, which is nice. Merely wrong in magnitude. It's significantly smaller than the turbulent one, which we don't understand. The formulas we've been using suggest there are supposed to be helicity hotspots. We haven't seen them in the shearing periodic systems. They may exist in other geometries. They may just be getting diffused away, though.
Sorry, the question to the previous part. So you always perform horizontal averaging in the plane of shear.
In the plane of shear.
Have you tried to do any kind of other averaging, for example, ensemble averaging?
If you put long realization,
We can sort of, if you look back,
Because you can lose some information that you
I mean, for example, like we have produced plots like this where we are correcting for the dynamo wave. So in situations like that, a time average, it sort of can be looked at as a time average, or at least you can look at this and sort of see time averaging effects.
but you can do it in-window average if you have got some typical.
We could do a moving window average here.
Yeah.
But we have done. We basically did. We took one of these, but you could shift it. It's not really see much change here.
The average over this, that's what we've done in this.
These two bars, like most of our data was taken from this band. Okay, so we took averages over this band.
Yeah.
We did not particularly shift the position of this band, but from this diagram right here and others that you can produce, it does not. There's really not going to be any obvious signal that you're going to get from shifting the window.
Does it mean, so what you find, maybe it's not true, Vishnik potol, maybe.
The Fishnet can show
It's
flux.
a total flux.
Our conclusion was that Fishnet can show flux is basically a gauge illusion. It's coming from the fact that they're operating in a gauge where A is not shearing periodic, and there are finite fluxes, horizontal fluxes. When you go to a gauge where where all the horizontal fluxes are eliminated, then you don't actually see any results. That actually comes like sort of the steps in the future that we're working on now, which is if you write out the flux of magnetic helicity as a function of phi, which is your chosen gauge, then there's an apparent preferential gauge here of phi is equal to A dot U, which converts the flux of magnetic helicity into an effective and permanently diffusive one. The gauge that we were working in has phi is equal to A dot U shear, which removes the components from the shear flow. We are actively working on actually putting in the full velocity field. And the results from that aren't really quite clear yet. But in conclusion, I want to say it'll be very interesting to know whether these oscillations here are real, or whether they're the result of fictitious helicity hotspots. But the introduction of a small amount of diffusion at least keeps your system, this right here has no diffusion, it keeps your system sane. So I expect we're seeing there is the generation of helicity hotspots, which completely blows up. So I'm worrying that these results right here are the result of not treating the horizontal fluxes in the system correctly, if you will. And I guess that's more or less it. The paper in question was short, so I tried to go a little bit beyond it. I could have presented the paper by saying fish tank control flux doesn't exist, and that would have been kind of boring.
And you haven't gotten any feedback from this?
We have a referee report which we'll actually need to get around to answering. The referee report is empty calories. Is the way I responded. Empty calories is the way I would characterize the referee report, which makes it empty calories. It's like we were talking about nutrition. Empty calories are sort of like sugar, the thing that don't actually really necessarily contribute anything. Referee report has a couple of lines. There's not that much of it, and it doesn't seem to be particularly. It's not going to responding to referee report is not going to drastically improve the paper.
Okay, then we should thank Alex first of all.
Let me ask again the same question. What happened with dynamic part of 5.5? Is it constant in this domain?
The forcing was constant throughout the domain, so there's no stratification on forcing.
No stratification, so but it's not zero. So integral of kinetic helicity in system is not equal zero.
Yes.
So gradient equals zero, you mean?
Yes, the gradients, all the gradients that do not, you could spontaneously generate some.
No, I speak about average. Average equals zero.
The average helicity, there is helicity input because the forcing was helical.
But even, furthermore, we can look at the gradient within the domain. And that's exactly what you said. So the small scale, for a small Reynolds number, there is a gradient. There's a pattern in the A dot B.
Yes, for small Reynolds number,
Locally.
there's something there.
And even then you don't have any helicity fluxes. And what you find is very, very small, in 10 to the minus 3 in non-dimensional units. And for the higher Reynolds number case, neither of them is present. And the fluctuations here are completely uncorrelated with the large scale field and are also small, below 10%. I think you should go back to the equation with the effective gauge. Next one maybe. Right. So that's, I think, of course, the point that the velocity enters really just in the form of advecting locally helicity.
And it's phi minus u dot b, a dot u, which is u again.
Sorry, say again?
You've got additional term, a dot u multiplied by b, which
Yeah, but this can be removed
by
the
gauge.
propagation.
Is it possible for any situation or just periodic boundary condition?
You can just run this with phi is equal to A dot U. And we're doing
You think it's okay?
Okay, in this paper, we were running phi is equal to A dot U shear. We are actively studying this case right now.
Okay.
This one is being studied. This right here
It
is
is,
what we're
so
learning.
it is, how to say, for large scale stuff it's true. For small scale, I think it's,
This right here, this choice, for reasons that we do not yet understand, appears to be numerically unstable. We're looking at that right now. We have developed a method to look at it that gets around numerical instability. And
I asked a question about last line, second line, not this one. Is it true for large scale magnetic field or just?
we were planning to
For any.
Okay.
Bar.
Not bar, era.
The full.
Okay. So
Not the full U.
you have here.
This right here is necessary to run this in a numerical scheme that uses the magnetic vector potential, and where you want the magnetic vector potential to be periodic or sharing periodic.
You consider here helical force.
Helical force.
Now, if you consider non-helical force.
Then we would not expect there to be an alpha omega dynamo.
Yeah, I understand.
So it'd be
But you
more
have
difficult.
shear dynamo.
If you can get a dynamo in a shearing system without helical forcing, then we could look at the transport of magnetic helicity. Although I would not expect it to be necessarily all that much magnetic helicity, since the dynamo is non-helical. It doesn't have helical forcing.
But the magnetic helicity plays very important role even for non-helical dynamo.
Yes.
If it exists,
Extremely important role.
yeah, then that.
Linearity is main.
But maybe it's good to try.
One other thing.
With that I fully agree, but then if the fluxes are, of course, and the fluxes are probably also important. The question is just where do the fluxes come from? Do the fluxes come from velocities? And if so, do they come from advection, in which case it's completely clear that they should of course work, or do they come from an effect which is different from just advection, namely shear? And that's exactly what is absolutely unclear, or it's clear that it shouldn't actually
One
come
thing
from
which is also important is, can the fluxes distinguish between large and small scale velocities?
But you
Which
know,
is a
if
crucial
you study
question,
this
and
first
it's
term
not
more
clear.
carefully,
Yeah.
you have got triple correlator, small scale triple correlator in this
Well, you can
equation.
also look at it as a double correlator.
No. If you open this
It's not worth going into right now. But it is worth. For what it is worth, we are part of the study of this right here involves treating small h as a scalar field.
let me demonstrate something to you. Maybe I demonstrate here in the previous my meeting. No. Let us study what actually happened with this guy. H means A, B, right? Multiplied by U small.
What?
A, B, U.
So this term right here.
Yeah,
this term
right.
That's what h is.
AB, small scale, and if you calculate it, it is one of the possible AB function of, say, some mean position plus V tau. V is a random again, VT. And then if you can replace by something ddx AB multiplied by VT, and this will be something V squared. T it will be, I'm sorry, diffusion. So this term reproduces diffusion
Yes.
in some sense.
This term right here
So
generates
diffusion.
mean advection and turbulent diffusion.
Turbulent diffusion. I would like to stress it. So you have got diffusion.
We have seen diffusive fluxes elsewhere, and this right here, we believe them. The question is, are there non-diffusive fluxes?
Non-diffusive flux
or non-effective. There's effective diffusion,
okay.
more or less the same thing. Are there other fluxes?
But it's, it is simplest interpretation of this.
That is
of course, if your talk takes sphere, for example, into account, or gradient of alpha, but you haven't, you say.
Yeah. So the question is, was there? I guess one of the questions we're looking at is, was there a Bishop control flux? We saw no evidence of it, down to like a parts in 1,000 or something. So.
And it's a still a calculation, of course, so it should have been valid even for small Reynolds numbers.
Yeah, so the Bishop control flux.
What about earlier papers, have nobody seen Vishniac-Control flux before?
It is incredibly difficult to look for the Vishniac-Control flux because the Vishniac-Control flux exists in a system of shear and exists for a gauge which doesn't really work well. So what people have done is they have looked at systems which could allow for a Vishniac-Control flux, seen better dynamo growth, and said maybe this is a sign that there is a Vishniac-Control flux.
But has the flux been actually, I mean,
The flux itself has not been seen by anyone, I don't think. Numerically. I do not actually object to the fact that the existence of the Vishniac-Control flux in the appropriate gauge, which turns out to be slightly fictitious or misleading.
so for example, if we use a different gauge here, for example, maybe the Coulomb gauge.
If you use a Coulomb gauge, we probably see it, but we can't. But running it numerically would be somewhat difficult and impossible.
Sure. But actually, what do you think? If we use a different gauge, do you see a Vishniac-Control flux?
I think we probably would. The problem is then we'd also see other fluxes. We see some
It would be
horizontal
very
fluxes.
interesting, but we have to go into a non-fluctuating periodic Coulomb gauge. And I don't think we have a technique really ready for doing that.
We don't, yeah.
Conversion.
I would conjecture that whatever gauge you go to, divergence of this flux will be same in all of them.
Yes, the divergence of the flux, that's something I sort of forgot.
The same.
The divergence of the flux is expected to be more or less gauge independent. So we are seeing no divergence of the flux.
And that's what I would conjecture.
Yes.
But you were just saying, there's an invert divergence.
Yes. So if you have the Vishniac, if you go to the gauge where the Vishniac-Control flux exists, then you also expect there to be a counterbalancing inwards horizontal flux, which negates it. But this would be extremely difficult to actually go and look for. So what we did is we went in the gauge where you could look, looked at the divergence of the flux and saw nothing.
Let me say so what about to flux in defense of this concept. If you nevertheless studied some, how to say, very idealized situation without gradient of density. So I think without gradient of flux. So my idea maybe if you take into account homogeneity, which is definitely typical for celestial bodies, it should be somehow restored.
Well, are you going to restore the Vishniac-Control flux, or are you going to produce another flux?
In the Vishniac-Control paper, they have a general theory and then they deal with a simple case, which they can kind of visualize.
Yes, again.
And in this simple case, it's only shear.
But he never studied periodic boundary conditions. It is very important point, guys. I think that we've got even shearing both periodic boundaries, and that's very specific situation. First of all, what's important in real bodies, we've got some kind of border with drastic change of parameters. If you take stars, if you take planets, if you take galaxies, so at least check it. Simple interest.
This situation
Maybe
here,
you're right. Who knows?
this situation here can still exist even for non-shearing periodic, but just shearing homogeneous shearing sheet.
It's the horizontal flux. If it's horizontal flux.
Especially at the large scale, but also I think at the small scales. It's just generally this.
Large scale, in some sense, large scale is fiction, if you like.
Okay, it's possible to do the following. To take system with shear, but with convection.
Right.
And in that case, you will have this
All
flux
stuff,
definitely.
all stuff, because you have got additional vectors of vertical
Well,
vectors.
You may well pick up a flux, but saying that it's a Vishniac-Control flux is another matter entirely.
I mean, the point is simply, if you have an inhomogeneous system, you certainly will have a diffusive flux. So now,
Non-diffusive. You mean difficult to distinguish.
Yes.
Difficult, but you can build this flux as function of differential rotation, for example, or shear band to say. And you will find part which depends on the shear.
It depends on shear, but you may not depend directly on the shear the way the Vishniac-Control flux, but you depend on the other vertical gradients and how they depend on the shear.
Okay, as far as I remember, when we discussed with Vishniak, when he the first time wrote this flux, he he tried to introduce the stratification.
Mhm.
that moment. So stratification was important.
Maybe important, maybe.
Yeah, it's not, as written up in the literature, it's not included.
It was not included in his paper, but yeah.
It- it's-
Yeah, they understood that may be important.
But again, it comes down to the fact that I believe his calculations. I believe that in the Coulomb gauge, you'll get the Fisher control flux. However, you are also dropping other flux terms, some triple correlators, some other obnoxious flux terms. And if you go into a gauge where those flux terms are eliminated, or at least the horizontal flux terms are eliminated, then you don't see anything that comes out. So any time you're going to a system where you're saying, we will isolate this portion of our, you have a gauge-dependent quantity, you're isolating one component of it, that's a very, very dangerous situation to be in.
Right.
Because your gauge choice can move things from one component to another in depressingly easy fashion.
Well, I might just add to the gauge thing. Actually, the equations look the same in the gauges, but of course, Vishnek flux changes in gauge, or not the equations.
The gauge control flux, as I remember, was calculated explicitly for the Coulomb gauge.
Yeah,
It's
exactly.
not
You
by
can
more
do more generally.
Okay.
It doesn't change. I mean, the pair will look the same.
Okay.
Look maybe at the formula again, or the mean field calculation rather, the picture of these two pendants.
This one?
Toward the end, I think, the mean field calculation. I want to show what happens to the different signs of us.
So there's
C,
going
C.
through.
Forward, faster, forward, almost at the end.
This one?
Further, here, before, backwards.
So you see, the effect of adding a Vishnek show flux is actually to decrease the saturation field strengths.
Yeah, regardless of what that actually exists in a mean field simulation, you can add it, whatever else happens.
So the fifth is what actually has a counterproductive effect.
No.
And the same is what, of course, Gustavo found.
Gustavo found the same.
But with a different figure, not with this one.
I probably should have gone with a different figure, but yeah.
Yes, maybe. So it's only when you have a negative sign.
Pump helicity into
Yes. Yes.
celestial
And even this effect is not very strong. We don't expect coefficients that are much, much bigger than that. Okay. So it's
So as far as the results is regarding the flux so far is concerned, there's no support of exactly those formulas that have been obtained so far. That's simply the point. There could be something which nobody has obtained yet, or no formula for that. But at least as far as this formula is concerned, there's no support for that.
And we do need to work on the actual formulas for the fluxes for shear because of the
Dashed lines here?
This right here is a mean field model without any diffusive flux. And as you may know, it was happy, and then it went crazy.
It's not exactly crazy. No,
Not exactly crazy.
It's the same result is obtained with higher resolution.
it's at the frequency of the dynamo wave.
But
And the amplitude simply goes down. It's the same behavior as here. So here you also see it goes down for around 1,000. This is also for 1,000, I believe.
And this is an alpha omega, right?
alpha omega.
Yeah.
So as we added basically adding almost any diffusive flux, completely suppressed that behavior, and made the dynamo behave very, very smoothly, which is one of the reasons why I'm a little bit worried about this behavior here, and think the actual DNS that could determine whether we actually have this or not would help us understand whether the fluxes are being adequately handled or not in the sharing.
Regarding DNS, I think at the moment we haven't even seen this peak yet. So I think what DNS may actually be showing so far is rather something like this. That it does go into a lower level, but it doesn't do it by this peak.
One thing that is worrying, I've seen some peaks, but those peaks are not due to the dynamo behavior. They're due to like some sort of velocity, maybe vorticity dynamo briefly. There's an early behavior stuff, which can be messy and it's not.
In your paper, you have that big thing.
In the other paper, yes. There is the other paper was A, not sharing, and B, I've done a lot of alpha omega dynamo simulations recently, and many of them have. We do not understand the alpha omega dynamo in a sharing periodic box yet. Just to let you know, I do not understand that at all. But there is frequently some fairly wild behavior in the early velocity field for an alpha omega dynamo in a sharing periodic system. So you can get the issue of initial peak is actually one that may be a little bit tricky to look at. The velocity field, but the velocity is not, in the systems that I run, the velocity is not steady in any useful, relevant fashion.
Any other comments or questions?
I think if we discuss real systems, a convective system, of course, if we calculate this tripods relator carefully, we will find lots of interesting things. And we will find, of course, something which proportional to flux thermal fluid.
What we are actually doing is we're actually treating it not as a triple correlator, but as a double correlator. We were basically treating H. One of the things we're doing right now, actively, is treating H as a scalar field. From which, and then you can treat H as an H bar plus an H prime.
You will find something.
And we're basically looking at that and trying to figure out, like, hopefully these ones are, I think, actively working on now, see whether the spectrum of that it looks like the spectrum of a passive scalar or not. And that is that's something that interests me greatly. I don't think it's actually quite as much immediately. But if it looks like a passive scalar, then you worry that there's only sort of a diffusive flux. If it's a non-passive scalar, then you immediately go, there is some non-diffusive flux in there somewhere.
Right. One of obvious non-diffusive flux, as Igor now mentioned, that is, of course, U divergence U, if you've got some compressibility issues in your system.
There may be some.
So
Yeah, this right here does generate.
Yes, okay.
Yeah,
Maybe it's called counterproductive. That's another story.
Yes.
But not only, I think there exists another possibility. If you've got, say, flux of entropy, it should be something proportional to flux of entropy. Flux of entropy.
Yeah, sure. Now the question is, would these fluxes live from the fact that you have shear or not? And that's not obvious.
It may be both. It may be combination, say, shear and this flux.
So actually, if you put a passive scalar in your flow, do you expect there to be pumping of a passive scalar?
Of course.
Okay.
It's known. Turbulent thermal diffusion was one of the examples of pumping of passive scalars.
Yes, right. So yes, using this, we can get the flux term down to a passive scalar plus unusual source terms.
Yes.
Unusual resistance source.
Yes, because it's magnetic.
Yes.
Right?
Okay, so thanks again, Eric.